Yes, the water jet. Okay, we've done this problem before where we're trying to measure the recoil force when water is being ejected from a fire hose. And as you can see, this fireman is having a pretty difficult time trying to stay on the ground because it's an incredible amount of force that is being generated, enough to lift up maybe over 100 kilograms of a person. All right, so what's involved in this problem? Okay, first of all, you need to know that the recoil force, like we talked about in the last problem, is generated by the impulse momentum relationship. Okay, and a key trick to solving the impulse that you're going to be getting, or the force that you're going to be getting, is understanding how to calculate mass flow rate. So if we go back and we write down the impulse momentum relationship, Ft is equal to my change in momentum. Okay, I wrote that down on purpose. Usually what we did was the Ft is equal to the mass of an object times its change in velocity. Okay, well, in this case, what we usually get out of a hose is a constant velocity of water coming out. All right, and what's changing is the mass of water that's coming out per second. Okay, so that's where you would have, if I had attached to the truck, there would be a dial telling me how many liters or kilograms of water is flowing through that hose per second. And if I know the mass flow rate, I can then rearrange this equation to calculate force. So take a second to see how you would rearrange this equation and applying a mass flow rate to calculate the force. Okay, so let's say this truck tells me that I'm getting 1,000, well, that would be a lot, 100 liters of water per second. Okay, so what's coming out of that jet is 100 liters of water per second. Okay, that's a lot of water coming out per second. Okay, so how do I convert that into a mass flow rate? Well, what you need to understand is 1 liter of water, because the density of water, so the density of water is equal to 1 kilogram per liter, or 1,000 kilograms per meter cubed, if you remember. Okay. Applying that, I would know that I have 100 kilograms of water coming out per second. So if I take a look at this impulse momentum relationship and I want to rearrange it, F is equal to M over T times V. Okay, so we have the velocity of water coming out, okay, the mass flow rate, all right, and so we calculate the mass flow rate being 100 kilograms per second. We have M over T, and all we need now is the velocity of the water coming out in order to calculate the force. Okay, so they would have to tell me in the problem what is the velocity of that water, how many meters per second is that flying, and I could set that up pretty easily. If we shot that water horizontally, you'd be able to see how far it goes. It becomes a projectile motion problem to be able to work out the velocity. Now that would be a challenging problem, but usually they would tell you the velocity of the water. So if I knew the velocity of the water and I knew the mass flow rate, I can then calculate the force. Okay. All right, so force, let's say that the water is flying at 3 meters per second, then I would have 100 kilograms per second times 3 meters per second. Okay, and then that should give you the impulse, okay, the force, kilograms meters per second squared. Okay, 300 newtons. That's not too much. Okay, so obviously the velocity has to be a lot more than 3 meters per second in order to lift that fireman. Okay, so that's one way of looking at it. Another problem that we've looked at before is, what if they gave us a hose? Okay, that's a hose, and they gave us the radius of the hose. Okay, and then they said that the velocity of water, okay, so if this is my water coming out, okay, if the velocity of that water is, let's say, 20 meters per second, okay, and the radius of the hose is equal to, let's say, 0.2 meters, how would I be able to use that information alone to be able to calculate the force? Okay, so if I go back and rearrange that equation, M over T, my mass flow rate, times velocity is going to give me the force. We have velocity, force is equal to M over T times 20. Okay, but then how would I use 20 meters per second and 0.2 meter radius to be able to calculate the mass over time, okay? So the trick here is to understand how would I calculate the mass of water coming out. If I had 20 meters of water coming out every second that has a radius of 0.2 meters on the hose, how would I calculate the kilograms of water that come out per second? Okay, and I'm going to give you a little trick. In 1 second, I get a length of 20 meters of water coming out. And let's imagine the water stays in a cylinder form. Okay, so I'm just going to draw out a cylinder. Okay, so I have 20 meters of water that comes out. Okay, that makes the length of the cylinder 20 meters. And the radius stays the same at 0.2 meters. Using those values, I can calculate the volume of water that would come out in 1 second. The volume of water, the volume is going to be equal to pi r squared. That's the surface area of that face, all right, times 20 meters, okay? That would be the volume. And if I look at the velocity here, that's going to be 20 meters per second. So if I multiplied the surface area here times the velocity, what I'm actually going to get is the volume per second is equal to pi r squared times my velocity. Okay, that's how much volume I'm getting out of water per second. So pi r squared times velocity. And if I want the mass over second, I have to just multiply the density of water, okay, in terms of meters cubed, times pi r squared times my velocity. Okay, and that would give me my mass flow rate. Okay, so the overall force formula would become density pi r squared times velocity, okay? Which the force would be the density times pi r squared times velocity squared, okay? And that formula there would allow me to calculate the recoil force. So density being 1,000 kilograms per meters cubed, pi, the radius in meters, so 0.2 meters squared, times 20 meters per second squared. So if I plugged all that in, okay, F is equal to 1,000 kilograms per meter cubed times pi times 0.2 meters squared, okay, times 20 meters per second squared. All that together is going to be able to calculate the force. And I'm sure that's going to be a much larger force than what we calculated above, okay? So just to review, okay, 2 ways of calculating this. If they gave me the velocity of the water, okay, and they gave me the mass flow rate, this is a very simple problem to solve. Okay, I just have to rearrange the equation, take the mass flow rate times the velocity, and that would give me the force acting on that hose. Or if they gave me the radius of the hose and the velocity of the water, we'd be able to derive this equation that we created here, okay, by finding the mass flow rate times velocity as we described above. The mass is determined by the volume that comes out per second, okay, the mass flow rate. The volume that comes out per second times density gives me my mass flow rate. Okay, volume is going to be pi r squared times 20 meters in 1 second, okay, times density would give me my mass flow rate, and then I plug everything in here, and I get this new expression. I've seen that question before on exams, and then you can plug the numbers in to calculate the force.